At this point, we've built up at this point, we've set ourselves up for a lot of success. We know that we're going to be picking lots of different types of logic to solve different kinds of puzzles. We've also told ourselves that some of the rules will be hidden inside of context. Things like which programming languages we pick, which books we're reading from, who we're talking to. But a lot of things have to be communicated explicitly, and for that we use grammar. Grammar is a surprising tool for mathematicians because it feels like something from an English class. However, it's essential that we think of our mathematical formulas as obeying a grammar. It's what makes all the communication reliable. But to really understand grammar, you have to know how to take it apart. If somebody writes an expression and you don't understand which grammar they're using, you won't successfully understand it. So we're going to do that step. It's called parsing, taking apart a sentence according to a grammar. I'm going to start with a few illustrations that don't seem at all related to grammar, and then we'll bump it up to the grammar that we need for logic. That'll be our final examples. But I'm going to start instead with something that you've done with numbers. So this is called factoring, and it has nothing to do with parsing, except the way the strategy works out will be very similar. Take a number like 24. If you were asked to factor 24, you'd have lots of choices to begin. I'm going to choose one, but you might try some of these other choices. I'm going to start by factoring a 6 and a 4. Once I've factored these, I then apply the process recursively. The idea is that my 4 and my 6 are being combined to build my 24. So now what combines to build a 6? A 2 and a 3. And what combines to build a 4? A 2 and a 2. So far this is straightforward. But here's the thing I want to get to. When do we stop? See, in principle, I could keep going from here. I could have 1 and 2. And then I could divide 1 as 1 and 1, and I could divide 2 as 1 and 2 again, and this process will never end. So, one of the key steps in factoring numbers is that we agree that there is some ultimate bottom that we want to get to, and those are the prime numbers. In fact, it also explains why we don't like to have 1 be a prime number, at least for this purpose. If 1 was a prime number, we would never stop. We could factor 1 as 1 times 1 times 1 times 1 times 1 and put a 1 on everybody. It would go on forever. If we remove 1 as an allowed number of one of the primes and we start primes at 2, it cuts this infinite regress out. And we now see that there's a perfectly clear, everybody follows, stopping point. The prime numbers are the end of it. So what we're going to do next is factor some formulas. And if we do this correctly, we should identify not only how we can factor them, the different operations we can put between them, but also the good stopping points, the primes, if you will. We're going to try to take this apart, similar to how we factored numbers, only we're going to factor this formula, this expression. If I stare at this formula from the very far back of my room, all I can tell is that there's a numerator and a denominator. Those are the most obvious, largest structure in this formula. And because of that, it's also a hint that that's the last thing we will do. We'll do a bunch of small micro steps to build the bottom and the top, so therefore the last thing will be this big step of making a fraction. And since that's the last step, that'll be the first thing we take apart. Similar to 24, we first took it apart into big pieces and then into smaller pieces. So I'm going to have an x plus 17, an x plus 7, and a 3 minus x. I'm simply copying my numerator and my denominator. Now there's a couple things that I'm going to do to add to this story to allow me to think of my parsing in a useful way. I'm going to go ahead and label between these two branches which operation I was doing. When we did this with factoring numbers, the only thing we were factoring was multiplication, so there was no need to be precise about it. But here I used division, so I'll use that old-fashioned division symbol right in the middle. I'm also going to pick a convention. The convention is that the numerator goes to the left and the denominator to the right. You could choose something else, but just be consistent everywhere. And since I read top to bottom and left to right, this seems to be the convention I like the most. I'll come back and later work on another property of this, which is that we don't want to divide by 0. That'll be our next thing. At this point, think of this as like analogous to our 6 and our 4. We can take them apart even more. Over here, I see that I have an x and a 7 combined with a plus. So I get x plus 7 as my two factors. But I also see that I could factor this. And now here I have some choices to make. I'm going to show you the two choices. First choice would be 3 minus x. And that's a perfectly reasonable choice because it's all the operations I see here. But one of the things that I've learned in teaching mathematics for many years is that minus sign can trip us up. There are lots of things about minus that we know are not quite the same as they are for plus. Let me demonstrate. Let's look at this addition of these three numbers. 8 plus 5 plus 2. What is it? You might say 15. The way I did that is I spotted that 8 and 2 could be put together quickly as 10, which is a nice decimal number to add to 5. Now let me try to do that same thing, but with subtraction. Here I run into trouble. If I do 8 minus 2, I end up with 6. And then I don't know whether I'm adding or subtracting that from 5. And if I do 8 minus 5, am I then subtracting the 2 from 5 or the 2 from the 8 minus 5? To articulate that, to show you that these are different answers, let's write it another way. We see that when you have 3 or more terms and just subtraction, it's unclear where the parentheses should go. Here I'll get 3 minus 2 to get 1. Here, this will become, because it's in parentheses, we do this first, this will become 3, 8 minus 3 will become 5. And those aren't equal. My point is, subtraction will get you into loads of trouble. So the better thing to do is never subtract, but instead, add a negative. So let's do that in this formula instead. You now see that I've made a plus sign and a minus sign out of it. It's the same algebra, it's just organizing it in anticipation that subtraction will be a problem. Nevertheless, we've achieved a factorization into what I might consider primitive functions, primes if you will. Why did I stop here? Well, similar to the number 1, once I have a variable, there's nothing more I'm going to do. If I'm going to use that, I'm going to substitute x with some number, and then I'm done. So breaking this up any further is just going to be unreasonable. For example, I could call that 1 times x. But just like 1 times 2 doesn't change 2, calling this 1 times x doesn't lead to anything new. So that's not worth extra effort. Also, constants, I might be able to factor a number, but I don't need to know the factors. I'm just trying to tell the simple functions. This is a constant function. For every input x, I just put the number 7 down, so I don't need to worry about refactoring that. So I would call this the end of the line. Now, let's get into some of the things we might learn from this parsing. When we parse something, we can start to put in the rules that will be necessary. For example, we prevent division by 0. To prevent division by 0, here, I need to backtrack and say that this must not be 0. And it helps me identify where I need to do some checks, either in my programming languages or in my reasoning. And now that this can't be 0, I have to ensure that whatever negative x is, when I add it to 3 doesn't become 0, I then solve for this not being 3. It's not that there isn't work to do, it's just that we're narrowing down where the work is happening. This parse tree now sees this entire formula in a way that everyone will get to the same final pieces and glued together in possibly different ways, but resulting in the same formula. That's our first parse tree. Now, we'll do a couple others to demonstrate some new techniques that will be incredibly important when we do the calculus, but we'll also see this in new situations like logic. What about this one? How do we factor this one? We see that there's sort of 2 parts. There's an outside part, which is a square root, and then there's an inside part, which is an x minus 7. So you're probably correct to predict that there should be a branch with an x minus 7, and another branch with a square root. But somehow we have to see how these 2 branches are glued together. What operation is hiding in between? The answer is composition or substitution. And I'm going to use the letter that's most common to calculus. It's known as U substitution. I put a U here and I assign U there. I'm simply telling you that this piece will be called U when it merges with that piece. The technical symbol for this is that little tiny circle that you used for composition. It's just like the division operator, it's gluing together 2 smaller pieces. Is this fully factored? Well, no, we can continue over here to factor this as x plus negative 7. On the square root side, I consider that to be another example of a primitive function. While it's also built from some different pieces, the square root is a button on my calculator and in my computer. I'm willing to think of that as a black box that I don't have to open up every time. Once I get to the square root, I'm going to go ask other things to reason about it. And when it comes to doing the calculus, the square root will be something that we'll have to come up with a rule for. If we want to do operations on it, such as these derivatives and integrals, we'll have to feature how to do it on this primitive function, and that primitive function. The rest will be how to glue it together. And that's the way that we break down much of the process. We parse the formula into smaller pieces. We work out algorithms for all the bottom pieces, the leaves, and we work out rules for combining them. This is a great strategy for breaking down a problem. Now, we're going to get to the calculus much later, but the calculus we're headed to first is our sequent calculus. It's the calculus we need to describe logic to each other. How do we tell people what we mean by our ands and ors and nots and ifs and thens and elses and all the things that we want to do to reason well? Let's see some parsing of those formulas. Okay, let's take a look at a new formula. I'm going to try to stress a sentence that we might say in a logical sentence. If rain, then wet, else dry. Now, I've left out many of the words that we might have in natural language. If it rains, then it will be wet, else it will be dry. Those are things we could add, but the articles aren't really part of the structure of the reasoning. So I've narrowed it down to what the computer and ourselves might need to know. So we see that there are three parts to this sentence. And then there are connectives, which are somewhat immutable. The if, then, else are the operations that combine three separate concepts. The concepts are rain, wet, and dry. These play different roles in the sentence, and they're interchangeable. I could change from if rain, then wet, else dry to if positive, then get paid, else work harder. Those are different concepts completely, but they fit in that if, then, else segment in the same way. So let's do the parsing that goes with this. We'll first divide this into three separate bins because there are three concepts being combined. On this one, we have rain. And this middle one gets wet, and then we get dry. The operation between here is if, then, else. It's a ternary operation. It takes in three values, three branches in our tree that combine to this part here. If we wanted to write this in our B and F grammar, we might write something like this. We'd have a conditional. That would be the sentence structure we have here. In our conditional, we would precede it by the word if. Then we would have a place where we put a value judgment, something that's true or false. Now, the study of true or false goes back to antiquity, but there's no denying that George Boole spent a lot of time refining our logic around the true-false and what its rules are. In honor of that, today, whenever we talk about true-false values, we reduce them to the word Boolean, after George Boole. So his name was just B-O-O-L-E. We just add the N to sort of turn it into an adjective. Boolean here means that it's a value that can only come to us as either true or false. Now, did it rain? True or false? Did I make money that day? True or false? Whatever the questions are, they're going to be reduced to that kind of a sentence. Once we have that, we want to say what we want to do. Then we'll have the effects. We have one effect if it happened and another effect if it didn't. That's the structure of our conditional grammar. Our conditional grammar accepts sentences that start with if, some phrase that comes from our Boolean family, then some effect, else some effect. Notice this does not tell us what will be the effects or what will be the Boolean. Those are the things we did in this color up here, which can all be substituted. But whenever we see an if then else, we'll factor it the same way. And it's not always written this way. Sometimes we use different symbols. Here are some alternatives to how we might write if then else. This top one you see in many programming languages. You put your Boolean in front, followed by a question mark. It reads as test if this is true. And if it is true, you give back the first answer. And if it's not true, you give back the second answer. It's not the same as if then else on the syntax. The letters have clearly changed from an if then to a question mark and a colon. However, they're exactly the same in terms of the philosophy. They're trying to measure whether this should give this or that. The syntax is being governed, the grammar is governing this, not the syntax. Another syntax might be something that a mathematician would write. They'd write a curly brace, they'd give the first option, and then afterwards write when that happens, if it rains. They'd write the second option as the second case and write else. And you can see here that you might generalize from if then else to an operator that's something many cases long. Select this when case 1, case 2, case 3, case 4, and so on. And you could also think about building that up to any number, even unbounded. You could even have a default case like the else at the very end of an if. What about removing some steps? Could we talk about an operator that's just if then without the else? Absolutely. You simply need to erase from your grammar the requirement of an else part of your clause. It becomes a binary, that means 2-valued operation instead of a single or instead of a 3-valued operation. The grammar then would change to something like this. We'd have conditional equals Boolean, whatever the symbol for transition is, maybe then, and then the effect. You can start to see that just the mere act of creating a parse tree, we're already pushing ourselves to think about what they might mean to do. When we write x minus 3 and we separate them, we think, oh, once I know a value for x, I'll add it to 3 or subtract it. Once I see if then else, I'm starting to think, if it rains, it must be wet. This is the key thing. Our simply symbol manipulation grammar is pushing us in the direction where we can start to think about what these trees will do. By being very precise about what the logic might have meant, about what the grammar might have meant, we can then move on to the real work of explaining what we want to reason about. Make sure that you can parse every formula that you see, and if not, go back and look for the grammar that's being used. Most of the time, it's something you've seen before, you've practiced with it. But if it's not there, look in your context. Find out where this operation was defined. Is there some part of the programming language where this is explained? Ask your scientific colleagues, what do these symbols mean? What is their grammar? How do I use them correctly? And then yourself, try not to be too sloppy when writing things. Sometimes we find many ways to abbreviate what we mean, but if we abbreviate too much and we break that grammar, people will have difficulty interpreting it correctly. Until next time.